Okay, guys, we're going to finish up the chapter. Actually, there's two more videos left, this one and one more. And we're going to finish up the chapter by talking about spontaneity, entropy, and free energy. Okay? So please, before we get started, I would like you to have a couple things out. And if you're watching the video, you're going to need to have your guided notes out, chapter 4 guided notes. We're going to fill out quite a bit of it today. And also, your thermodynamic data tables, that packet that I gave you in class. There's also some thermodynamic data tables in the student workbook if you don't have that packet. Okay, so what we're going to learn today is what is spontaneity? What is a spontaneous process? And what determines whether it will be spontaneous? Okay, that's what we're going to learn about today. Really, we're going to talk about entropy. So after today's lesson, you should be able to know what spontaneity and entropy is. The next lesson is going to be about free energy. So we won't talk about free energy today. So in this part of the chapter, we're going to look at what determines which way a reaction will proceed. Will it go on its own from reactants to products? Will it be spontaneous? During the next chapter, so chapter 5, we're going to actually talk about what determines how fast the reaction will occur. Okay, so let's get started. Spontaneous. A spontaneous process. You're supposed to write this in your notes. It's one of our vocab words. A spontaneous process is a process that occurs without outside intervention. So when I think of spontaneous, I think of a process that will happen on its own. It just happens on its own. Thermodynamics can tell us the direction in which a reaction will occur, but it can't say anything about the speed of the process. So in this next couple lessons, we're going to learn if a reaction can occur on its own, and whether it will be spontaneous or not. But it doesn't tell us how fast that reaction will occur. For example, rust. Does iron rust on its own? Is it spontaneous? It is. But how long does that take? A long time. It can take decades. And so we're going to learn about whether a reaction can be spontaneous. But just remember, as we're going through these problems, it doesn't tell us how fast it's going to occur. So we are going to need both thermodynamics and kinetics to describe a reaction completely. So we'll learn kinetics next chapter. Here's the deal. Thermodynamics compares initial and final states. When we drew an energy diagram and we put enthalpy on the y-axis and reaction time on the x, we start up here where there's some activation energy. It comes down here. The reactants are up here. The products are here. All we're concerned about in thermodynamics is initial compared to final. So we talk about this delta symbol a lot. But next chapter, we're going to go and describe what the pathway between the initial and the final. This is really what determines how fast the reaction occurs, the activation energy. Okay, so back to spontaneous reactions for a second. I've got a couple of pictures up here on this slide I would like to go through. First of all, let's talk right here. We've got a solid piece of iron. If you leave iron out in the open and in the weather, it's going to react with the oxygen in the air and the water when it rains, and it's going to form rust. What is rust? Well, it's a compound. It's iron oxide. So this iron is going to become oxidized and form rust. Now, does this process happen on its own? Is it spontaneous? Yeah. It is. This is a spontaneous process. It doesn't need outside help. But think about this. Can you ever see rust go back to a clean, pure piece of iron? No. At least not on its own, right? I mean, you can see that happen, but it's not going to be on its own. That's what we call a non-spontaneous process. So, you see this all the time where there's this old car out in this field. It's all rusted over. Can it ever look like that again?
Yeah.
It can. But is it going to be a spontaneous process?
No.
No. That's going to take a lot of energy and a lot of, you're going to have to work on that a lot to make it look restored again. So that is not a spontaneous process. Okay, here's some examples of spontaneity. A ball. If you have a ball at the top of a hill, will it roll to the bottom on its own? Yeah. That's spontaneous. Can you ever get the ball back up on top of the hill? Yeah, but you have to do what? You have to push it. You have to pick it up, and you have to use energy to get it back to the top of the hill. Okay, but spontaneously, it will roll down the hill by itself. Steel, when it goes to rust, is that spontaneous? Yeah. You will never see rust go back to steel on its own. Okay, so that is non-spontaneous. What about if I sprayed some perfume or some cologne up here? Would it spontaneously move throughout the room? Yeah, and in about a couple minutes' time, everyone in the back of the room would be able to smell it, right? Because the gas particles had moved and they had dispersed throughout the room. That's a spontaneous process. Now, can you ever get the reverse to happen where all those gas molecules come back into one corner of the room? No, that's not going to be a spontaneous process. Heat flow. Heat flow always goes from hot to cold. Will you ever see heat go from cold to hot?
No.
Not on its own, right? Not on its own. So always from hot to cold, that's spontaneous, but not the other way around. Okay, wood, when you burn it, does it spontaneously form heat and CO2 and water? Are these the products? It's spontaneous. When you light wood on fire, it's spontaneously going to burn and produce those products. What if we took CO2 and water and heated them up? Would it spontaneously go back to wood? No, that would be non-spontaneous. Okay, so let's talk about what causes a process to be spontaneous. Really, the driving force for a spontaneous process is the increase in this property we're going to talk a lot about today, entropy. Now, it sounds like, and it kind of looks like enthalpy. Remember what we talked about at the beginning of the chapter? Enthalpy, which is heat energy. But this is very different. Entropy is different. So entropy is really the driving force for whether a reaction will be spontaneous or not. So let's look at what entropy means. Here it is. Entropy is given the symbol capital S. So whenever you see this capital S in this chapter, you're going to think about entropy. Now here's the definition. Entropy is the measure of disorder or molecular randomness. It is the measure of disorder. That's how I think of it. I'm going to say that a lot today. Measure of disorder. So if entropy increases, we get more disordered. If entropy decreases, you get more ordered. Okay, so think of it in these terms. Entropy is the measure of disorder. Okay, now the natural progression of things is to go from order to disorder. That's just how nature is, right? You're going to start with something that's very ordered, and nature will cause it to become disordered. Like, for example, if I took a stack of papers outside, it's nice and ordered, okay, and I've got them all in order. If I leave it there, nature, is it going to leave it in a nice ordered form? No. The wind's going to come up, somebody will take them, and it's going to scatter, the wind's going to scatter them, and it's going to become disordered. That's just the natural state of everything, is to become more disordered. Like, think about your room, okay? Is the natural state of your room clean, or is it messy?
It's actually clean.
The natural state of your room is messy. What do you have to do if you want to clean it? You have to work on it. You have to put energy into putting things where they need to go. But the natural state of things is for things to become more messy or more disorder. Okay? So let's talk about why that is. Oh, here's another example. A deck of cards. If I had a deck of cards up here and I shuffled them, let's say I shuffle them 3 times. What's the probability that after I shuffle them 3 times, that they're going to be in order? Like the 2s are all going to be in order, the 3s are going to be next, the 4s and the 5s and the 6s. What's the probability of that happening? Very, very small. Now, is there a probability that that could happen? Yes, but it's so small. So we're going to talk about probability for the next couple of slides. All right, I really like this this sign of entropy, guys. This is a perfect way to describe entropy. Look at the E on entropy. Is it nice and ordered? Yeah. But what's happening as you continue on with the letters in this word? It gets more disordered. Isn't that what entropy means? Entropy means it's a measure of disorder. So as you continue on in that word, it gets more disorder. That's exactly what entropy means. Okay. Let's look at this. If I open this valve in this container, and these are gas molecules here, if I open this valve 5 minutes later, is there a very high probability that they're all going to be right here still? No. Most likely, in terms of probability, these gas molecules will be spaced throughout the whole container. Okay, so let's answer this question, guys. Let's see if you got this. Which phase, solid, liquid, or gas, has more entropy?
Gas.
When I say entropy, you should think what? Disorder. Which one has more disorder? The gas phase. How come? That's right, but how come? Yeah, if you look at the solid phase, these molecules are right next to each other. It's very ordered. It's a very ordered phase. Liquid, a little more disorder here, but not as much as the gas. I mean, they're very far apart. There's a lot more disorder in the gas phase. Okay, please remember that. As we go through these problems, which phase has the most disorder? Gas phase. Has the highest entropy. Okay, let's talk about entropy in terms of probability. Substances will take the arrangement that is most likely. The most likely is the most random. We're going to calculate the number of arrangements for a system in the next couple of slides. Now, let me explain this. This is just an open container here. It's got 2 sides, left and right. And this is a molecule. One single molecule. Let's say we let this go for 5 minutes. And you come back and you could pause time and find out which side this molecule would be on. What's the probability that it's going to be on the left side, for example? 50-50. So there's a 50-50 chance. What's the probability that it will be on the right side? 50-50. So in terms of this happening, it's just like flipping a coin. Whether it's on the left or right is not more likely. It's equal, 50-50. Okay? So who knows? It's a coin toss here. But let's talk about probability in terms of this. Now I've got 2 molecules. You let it go for 5 minutes, you come back and you can pause time and find out where they're at. What scenario has the most probability? Like, what's more likely here? When you come back in 5 minutes, what's the probability that they're going to be on the right side? How many total choices do we have? 4. So the probability that they're on one side, what's that? Well, couldn't this be on the same side on the left or right?
So 50%.
So that's 2 out of 4, which is equal to 50%, right? What's the probability that they're going to be on separate sides? So one on each side? 50%. Okay. So what's more likely? I kind of explained this bad, didn't I? Because now it's the same. Okay, let's restart that. And it's on video, yeah. Okay, let me see if I can explain this again, because that shouldn't be the same. Let's say you come back in 5 minutes. What's the probability that they're both on the right side? 1 out of 4. So that's how much percent? 25%. What's the probability that they're going to be on the left side? 1 out of 4, and that's 25%. Now, when you come back, what's the probability that these molecules are going to be on separate sides?
50.
Yeah, 2 out of 4, which is 50%. Okay, so that's exactly what we're talking about here with entropy. Which one is more disordered, guys? Yeah, the middle two, when they're on separate sides, it's more disordered. Well, that's why entropy favors disorder, because there's a higher probability for it to be disordered. For them to be on one side, this becomes more ordered. It's less probability that that will happen. Okay. All right, let's try it one more time. Okay. What's the probability that when you come back in 5 minutes, they're going to be either on the left or the right side? What's the probability? How would you do that? Well, left or right side, how many possible choices are there? 2 out of how many? 2 out of 12, which is equal to 1/6. There's a 1 in 6 chance that that could happen.
17.
What's the probability that 3 will be on one side and 1 will be on the other side?
It's like
That happens here. 1, 2, 3, 4. So 4 out of 12, which is 1/3. A little bit higher probability, right? But what's the probability that when you come back in 5 minutes, there's going to be 2 on one side and 2 on the other side? So we got 1, 2, 3, 4, 5, 6. Out of how many? Which is 1/2, yeah. 50% chance. So entropy favors disorder, and here's why. It's just a higher probability for molecules to be more disordered. Nitroglycerin. This is a very explosive molecule that decomposes according to this equation. So let's look at it. This is nitroglycerin right here. Which phase is it in? The liquid phase. How many moles do I have? So we have 4 moles in the liquid phase on the reactant side. When it decomposes, it forms nitrogen. How many moles of nitrogen? 6. In which phase? Gas phase. It also forms carbon dioxide. How many moles?
12.
In which phase? The gas phase. It also forms water vapor. 10 moles in the gas phase and oxygen 1 mole in the gas phase. Now if you look at this reaction and think about it in terms of entropy, which side is more disordered? The left side or the reactant here? Or the right side, which are the products? The products are way more disordered. Okay, because we got 4 moles, which are in the liquid phase, which is more ordered. Now, when we end up, nitroglycerin forms all these products. How many moles do we have? What's 6 plus 12 plus 10 plus 1? What is it, guys?
29.
There's 18 plus 10 is 28, 29. So we got 29 moles. In which phase? The gas phase, which is more disordered, and we got way more moles. So that's why nitroglycerin is, there's just so much, disorder in the products that it's going to be favored to go that way. It's going to be spontaneous to go that way. And that's why it's so dangerous. It's really a dangerous chemical to handle. Here's a piece of, it's a stick of dynamite. Nitroglycerin is the active ingredient in dynamite. In fact, you can set it off if it's unstable enough, even just by a loud noise, some vibration around it. Okay, and then it forms all these moles of gas, and it just expands quickly. And it's just a huge explosion. Okay, let's see if you got this. Practice problem number 25. It says, for each of the following pairs, choose the substance with the higher entropy value. Higher entropy value. What does that mean? More disorder or more order?
More disorder.
more disorder. So you guys tell me, on A, solid CO2, which I guess would be dry ice, or CO2 in the gas phase? Gaseous CO2. It's way more disordered. It's way more disordered. Okay, part B. Nitrogen, now this is an interesting one you're going to have to think about. Nitrogen gas at 1 atmosphere of pressure or nitrogen gas at 1 times 10 to the minus 2, which is 0.01 atmosphere of pressure. What does pressure do to a gas, guys? It compresses it and makes it more ordered. Closer together is ordered. Well, if there's less pressure, can't these molecules spread out more and become more disordered? So what would you circle here? Yeah, it's the nitrogen gas at a lower pressure. Okay, did we get it right? Practice problem 26. Stay with me, guys. This one says, predict the sign of entropy change for each of the following processes. A. Now this one I want the entropy change, the sign of the entropy change. If it's positive, if S is positive, it's going to be more disordered. Okay, so think about that. Let's do A. Solid sugar, so let's say you have a sugar cube, and you add it to water to form a solution. Is it going to become more ordered or disordered? Disordered. So what's going to happen to the sign of entropy? Positive. Good. So A is going to be positive change. You're increasing the entropy. You're increasing the disorder. Okay, what about B? Iodine vapor, which is a gas, condenses on a cold surface and actually forms crystals.
Negative.
Good. How come it's negative? Yeah, it's becoming more ordered. So S is negative. So always remember, entropy is disorder. If it's going to increase, it's got to get more disorder. If it's negative, it's getting more ordered. Okay, did we get it right, guys? On A, it was positive. On B, it was negative. Very good. Now we're going to look at something a little bit different. I want you to predict the sign of the change in entropy. Remember that entropy is a measure of disorder. Consider this following chemical reaction. Let me show you how to do this. If we had this chemical reaction, let's look at a couple of things. How many moles of nitrogen do I have right here? 1. Which phase? Gas phase. How many moles here? 3 in the gas phase. So let's answer this question. How many moles total for the reactant side? 4. So 1 plus 3 is 4 for the reactants. How many moles total for the product side? 2. And it's in the gas phase. So 2 moles here. Now, 4 moles to 2 moles. Is it becoming more ordered or disordered? We had 4 on this side. It's got only 2 on this side. It's becoming more ordered. Okay? So, if we look at this, the reaction became more ordered, or the entropy is negative. So if I asked you the sign of delta S here, I hope that you would say that the sign is going to be negative. It's getting more ordered. Okay, we can see that. There was 4 moles of gas here, only 2 moles of gas here. Okay, practice problem 27. Let's see if you guys can do this. Predict the sign for the change in entropy for each of the following reactions. So I'm going to put them up right here. I would like you guys to try this on your own. In your notes, tell me whether the sign is going to be positive for entropy or negative for entropy on both A and B. Let me give you some time to do that. If you're watching the video, please hit pause. Try it on your own first. Okay, let's see how you did. Hopefully you gave it an honest effort and you said whether the sign was positive or negative for each of these. Now, let's see if you got it right. Okay, on A, here's how I would look at a problem like this. We had 1 mole in the solid phase. So the 1 mole in the solid phase is now becoming 1 mole in the solid phase plus 1 mole in the gas phase. Is this getting more ordered or disordered to you guys?
Disordered.
That's disordered. Now we're adding a mole of gas. So the sign of delta S is positive because it's getting more disordered. Let's see how you did with B. We've got 2 moles in the gas phase, 1 mole in the gas phase, so we got 3 moles in the gas phase, becoming 2 moles in the gas phase. So now we're getting more ordered. So hopefully you put here that your delta S is going to be negative. Okay. I want to see who got it right. Who got it right? Good job. If you missed it, do you see why you missed it? If it's becoming more disordered, that's what entropy measures, is disorder, it becomes positive. If it becomes more ordered now, delta S is negative. Okay. Hey, but guys, hey, it's not quite good enough for chemists just to say whether entropy is going to increase or decrease. We actually want to quantify this value. We want to put a number to it. Chemistry is very precise. So let's learn how to put a number to entropy. Okay? So the entropy of a reaction can be calculated by the following equation. Here's the return of the Big Mama. Okay? The return of the Big Mama equation. Okay, so the return of the Big Mama equation, we've seen it before, so it should look familiar. But if you're calculating the change in entropy for a reaction, it's equal to, you're going to see the sigma sign, which means take the sum of. NP is the number of moles of product times the entropy value of that product minus the sigma sign again times the number of moles of the reactant times the entropy value for each reactant. So the general form again is we're going to take products minus the reactants. Products minus the reactants. Now, where do you get these entropy values from? The tables. Yeah, these thermodynamic data tables, that packet that I passed out. Please have that out for the next few slides. Where do you see the entropy values listed on these tables? Where is it?
The first column. The first number. Third row.
Wait, there's a last.
It's in the last column, isn't it?
Yeah.
See that entropy sign S? We're going to look up those values. Okay? Now, what do you notice about the units of those values?
Joules per mole.
It's joules per mole Kelvin. K is for Kelvin. So pay attention to the units. Now this one's in joules. Okay. Let's go through an example problem. I'm going to work this one with you guys. Okay? So it says calculate the change in entropy. The change in entropy at 25 degrees Celsius for this reaction. Do you guys remember what this little looks like a degree sign? Do you guys remember what that means? That means standard state. So that little degree sign tells us it's in standard state. What is standard state, guys? What temperature? 25 degrees Celsius. How much pressure? 1 atm. Okay? And since we're at 25 degrees Celsius, we are at standard state. So they're going to put this little circle there. Okay? Now let's just follow the Big Mama equation and do this. My delta S for the reaction. Please write down everything that I write down. Is equal to. I started off with the bracket symbol. Now, do we do the products or the reactants first? The products first. How many moles of SO2 do I have?
2.
2. So I'm going to put a 2 right here. Now what do I put next for SO2?
2.
I've listed them here, but you could look them up in your thermodynamic data tables. Is it 248? Yes. So 248 is the entropy value for silicon or sulfur dioxide. Now the sigma sign says you take the sum of. So we're going to add this to my other product. How many moles of this product do I have?
2.
2. NiO has the entropy value of 38. Okay, is that all of my products now?
Yeah.
Yeah, so close it off with the brackets sign. Now what do you have to do with the reactants?
Minus.
You got to subtract them. So we're going to put a minus here. Start another bracket symbol for your reactants. How many moles of NiS do I have? 2. And NiS has the entropy value of 53. The sigma sign in that equation tells us to take the sum of, which means we're going to add it. How many moles of oxygen do I have? 3. So we take 3 right here and times it by its entropy value of oxygen is what? 205. Now, a key difference I want to explain. If you were talking about enthalpy, what would the delta H of formation for oxygen would have been? It's a free element. It would have been what? 0. But entropy doesn't follow that rule. Okay, so that's a key difference. Entropy will never be 0. So you've got to look everything up. Now let's take a second and simplify this. It's just a simple math problem now. So 2 times 248 becomes 496 plus 2 times 38 is 76. Keep the minus sign in. 2 times 53 is 106 plus 3 times 205. Did you guys get 615 right there?
Yes, sir.
Okay. Now let's simplify that. What we have there. 496 plus 76, 572. Minus 106 plus 615 is 721. Okay, now simply 572 subtract 721 is equal to, now this was a delta S, which is change in entropy, is equal to a negative 149. Now what are my units going to be?
Joules per Kelvin.
If you look at your table here, we have joules per Kelvin mole. Now we have already accounted for the moles because we've times it by the number of moles. So we just need joules per Kelvin. So we'll just write joules per Kelvin. And this really tells us that we're at 25 degrees Celsius, which is 298 Kelvin. But anyway. Now, before I move on to the next slide, what does this tell us? The change in entropy was a negative 149. Did we get more ordered or disordered?
More order. More disorder.
One of them.
What does entropy measure, guys?
Disorder.
Disorder. So if it's disorder and if it's positive, it gets more disorder.
Yes.
But this was negative, which means what?
Order.
It got more order. Let's look and see if that's really what happened. I had 2 moles in the solid phase. Well, I had 2 moles in the solid phase over here, so that's kind of a wash. I had 3 moles in the gas phase. Now I only have 2 moles in the gas phase. So did it get more ordered?
Yes.
It did. And that's why you see a negative entropy value. All right. We did get it right. Practice problem 29. I would like you guys to try this one on your own and see if you can get the right answer. Please give it an honest effort. I'm going to give you some time, so if you're watching the video, please hit pause right now. Try it on your own. I'm going to solve it, so please try it on your own, hit pause, and then once you have an answer, hit play. Okay, so I went ahead and solved it, guys. And I hope that if you're watching the video that you did it as well, and this is the number that you got. So my change in entropy was a positive 179 joules per Kelvin. Now, what does that really mean? It has a positive entropy value. What is that telling us?
Disorder. That it's getting disorder.
That the reaction got more disorder. There's more disorder in the products than there was in the reactants. Let's see if that did make sense. We had 1 mole of a solid. Now we have 2 moles of a solid. So 3 moles of a gas, and now we have 3 moles of a gas. And so it did become more disordered. Okay, and that's what this positive entropy change is telling us. It got more disordered. Okay, final slide of this lesson. This whole chapter has been about thermochemistry, and we've been studying thermodynamics. Well, there's actually 3 laws of thermodynamics that I would like you guys to know. The first law of thermodynamics. And you do have to write something in your guided notes here. The first law of thermodynamics states that the energy of the universe is what? Energy of the universe is constant. This goes back to the law of conservation of energy. Can we create energy?
No.
Can we destroy it?
No.
We cannot create nor destroy energy, so it's constant. But guys, can it change from one form to another?
Yes. Yeah.
Yeah, typo there. States. That's supposed to be states. Okay. Energy of the universe is constant. Second law of thermodynamics is exactly what we've been talking about today.
Yeah.
States that in any spontaneous process, there is an increase in entropy of the universe. The entropy of the universe will always increase. If it is a spontaneous process, entropy is going to increase. So as time goes on, the universe, guys, is getting more and more disordered. Because that's just the natural state of things. It tends to form disorder. Okay, final law of thermodynamics states that at absolute zero, which is the coldest temperature you can reach, absolute zero is 0 Kelvin. A pure substance, it will exist as a perfect crystal. So everything will be perfectly ordered. No molecular motion will happen. It's too cold, molecules actually stop moving, so there's no energy. At temperatures greater than 0 Kelvin, entropy must be greater than 0. So if there's any heat energy at all, the molecules are going to move, and if they move, there's disorder. So entropy will be greater than 0. If you look at your data tables, and you look at those entropy values, this far right column, you will never find something that is 0. Okay? Entropy, there's always a measure of disorder, because there's always energy, and there's always motion, and things are in constant disorder. So if you look through there, you'll never see an entropy value of 0. Okay, that's it for this lesson. Hopefully you've got a better idea of what makes a reaction spontaneous, which means it will occur on its own, and how to calculate entropy, which is a measure of disorder. Before we quit, guys, I wanted to give you an opportunity to try some of these problems on your own. So in your student workbook, there's a worksheet called Spontaneity and Entropy Worksheet. So let's go there. Again, it's called Spontaneity and Entropy Worksheet, and hopefully this video helps.